Assalamualaikum and a good day. I am Hidayah Ismail with matrix number 193936, currently a final year student in Bachelor of Aerospace Engineering. The title for my FYP is The Effects of Seat Pitch and Body Anthropometry on Aircraft Passengers' Sitting Comfort. Here is the presentation outline where it consists of introduction, objectives, methodology, results and finally the conclusion. As for introduction, seating comfort is one of the most important factors that has been considered by flying passengers. The growing number of passengers have led many airlines to reduce the seat pitch in order to fit in greater number of passengers in each flight by increasing the number of seating rows into the cabin. Anthropometric's contribution does affect passengers' comfort in the cabin, where it explains that passengers might be able to receive comfort according to their body dimensions. In fact, anthropometry parameters of passengers' body also changing and becomes bigger. Therefore, there are many complaints of in-flight discomfort due to low legroom space. Low available space and legroom are very significant in generating the passenger's discomfort in flight. This implies that there is a mismatch between seat pitch and passenger's body anthropometry dimension. After all, it is of high interest to establish the influence of seat pitch and passenger's anthropometry parameters towards in-flight seating comfort, and eventually it will help to improve the cabin design setting. The main objective of this research is to study the influence of seat pitch and passengers' anthropometry parameters on their in-flight seating comfort. The following two study objectives are outlined to support the accomplishment of this study goal. The first one is to conduct seating comfort experiment inside an aircraft cabin mock-up with varying seat pitch and anthropometry parameters. Then, the study continues to analyze the effect of seat pitch and body anthropometry dimensions on the seating comfort level of aircraft passengers through statistical analysis. Here is the brief methodology of the study, which is starting from pre-study, then continues with the experimental conduct, and finish with establish the effects of the seating comfort using the statistical analysis. Here is the conduct of anthropometry measurement. Due to the challenges of COVID-19 pandemic and MCO by the government, only 30 voluntary participants are able to be gathered among the Malaysian public for this study. Two anthropometric measurements that have been identified in literatures as influential to aircraft sitting comfort are crown buttock height and buttock knee length. The summary of collected data is as tabulated, where the mean of crown buttock height for male and female are 87.2 cm and 80.2 cm respectively, while the buttock knee length of male and female are 57.3 and 55.8 cm respectively. This is the seating comfort assessment. Initially, in pre-study, 4 volunteers were enrolled to construct the seating comfort assessment tool for this study. The volunteers were asked to sit on the aircraft cabin mock-up and took note on the factors that affect their seating comfort level as the seat pitch was varied. During the discussion after seating session, the volunteers shared that factors that influence their comfort feeling for different seat pitch. Therefore, the outcomes from the discussion are used to construct the questionnaire for the seating comfort assessment in the actual experiment. Continuing the previous slide, the assessment of the seating comfort is done using a questionnaire that is constructed based on the received feedbacks in the pre-study. The participants are asked to rate their agreement to the statements in the questionnaire with regards to their seating comfort level. A standard 5-point Likert scale is used in the assessment, where 1 indicating strongly disagree while 5 is strongly agree. The comfort elements that have been asked in the questionnaire are about postural sensation, spatial perception, present mood, mobility, and final one is the overall comfort. Next is the experimental setup. The seating experiment is conducted using the aircraft cabin mock-up in Aerospace Design and Simulation Laboratory, University Putra Malaysia. Firstly, the crown buttock height and buttock knee length of the participants are measured. The participants are briefed with the procedures and expectation of the experiment before they start the process. The participants are assigned to sit on the aircraft seat for 10 minutes for each session, and after that, participants are required to fill up the comfort assessment questionnaire at the end of each session. The participants are free to sit at their own preferred sitting position or posture throughout the experiment. Here are the four results that has been analyzed statistically by the study. The first one is the influence of seat pitch towards spatial perception and postural sensation. Second one is the influence of seat pitch on mobility. Then the influence of crown buttock height and seat pitch on mobility. And the last one is influence of buttock knee length and seat pitch on the overall sitting comfort. Here is the first one, the influence of seat pitch on spatial perception and postural sensation. As the figure on the left-hand side, the blue result is showing as the seat pitch increases, subject's perception towards the coziness of the sitting row also increases. However, at certain limit of seat pitch, starting at 38 inches of seat pitch, some of the subject rated that they have less comfort if the sitting row is too wide. This might relate to the privacy of the subject. Nevertheless, according to the red result, as the seat pitch increases, subjects will not feel restricted anymore to the front seat view. Subjects no longer feel like sitting in front of a wall. Then the graph on the right hand side is about the influence of seat pitch towards postural sensation. The blue graph explains that as the seat pitch increases, it becomes easier for the subjects to adopt comfortable sitting posture, while the red one, which is the ability to change the sitting posture, also increases in the growing seat pitch. Both variables of the postural sensation were highly correlated to each other based on the Pearson correlation analysis that shows R is equals to 0.977. The next result is the influence of seat pitch on mobility efficacy. On the horizontal axis, it shows that the statements of the mobility action where A is the easiness in moving through the sitting rows, B is the ability to bend the upper body, C is the sensation to stretch out the body to the maximum comfortably, and D is the ability to lean head forward. This graph has demonstrated that the difficulties on the mobility level of subject is higher at low seat pitch. However, as the seat pitch increases, higher mobility efficacy can be adopted by subjects for graph A, B, and C, which proves that the first three graphs has positive correlation towards seat pitch. On the other hand, for graph D, the ability to lean head forward to the front seat has shown negative correlation towards seat pitch. This is the influence of crown buttock height and seat pitch on mobility comfort. Both figures, which are the surface response on the left-hand side and the contour plot on the right-hand side, depict that in increasing seat pitch and crown buttock height, the mobility comfort can be adopted by the passengers. The result has summarized that passengers with crown buttock height 80 cm achieve most comfortable mobility posture at 35 inches of seat pitch, while passengers with crown buttock height 86 cm and above, they are able to adopt most comfortable mobility posture starting at seat pitch of 38 inches. However, at seat pitch of 41, all range of crown buttock height can adopt mobility comfort. Contour plot gives better view and explanation that as the seat pitch with crown buttock height higher, the mobility comfort also become high in score. The transition from blue to green indicating that mobility comfort can be adopted as the seat pitch increases. The last result is on the influence of buttock knee length and seat pitch on overall sitting comfort. From the surface response graph on the left hand side, it seems that the buttock knee length is influencing the overall comfort in the growing seat pitch. The graph presents that for passengers with low buttock knee length from 50 to 56, the optimum seat pitch will be between 32 to 35 inches. Beyond that, the overall comfort starts to reduce due to less privacy. While for passengers with buttock knee length above 56 cm, comfort increases with increasing seat pitch where mostly achieve maximum overall comfort at 41 inches. In summary, the contour plot has shown that at very low of seat pitch, which is 26 to 29 inches, passengers rated the overall comfort is hard to be achieved. But as the seat pitch rise, the overall comfort can be achieved depending to the passenger's buttock knee length. In conclusion, seat pitch, crown buttock height, and buttock knee length have been shown to be significantly affect the in-flight sitting comfort level of the passengers. From the observed trend of their effects, there is an optimum setting of seat pitch such that the sitting comfort can be maximized for the majority of the passengers. In recommendation, for future work, more experiment data should be collected and a proper regression analysis can be conducted statistically to derive the mathematical model of the effect on the passenger's sitting comfort. However, this model can be then used to optimize the setting of the seat pitch for improved passenger sitting comfort level. That's all for the presentation. Thank you.